This video is going to talk about gravitational potential energy, but before we talk about that, let's take a short step back and look at what has work done for us so far. We've really looked at it in two contexts. In the first one, we have talked about work, force acting through a distance, makes something speed up. Makes something speed up. Okay, in this case, the force is a constant force, and the force is in the direction of motion. So it's just going to be simply work equals force times distance, and then we see this thing is moving now, where it wasn't before. Okay, so now it has kinetic energy. We wanted to quantify that. Well, it turns out that the amount of work you do, force times distance, constant force, can be shown to be equal to 1/2 times the mass of the object moving times v squared. Now this is if the initial velocity was 0. If it was already moving, then this would be 1/2 mv squared final minus 1/2 mv initial squared, etc. Okay, that's work and kinetic energy. Work and kinetic energy. And this guy, this is the one there. If you want to quantify the amount of energy something has, it's 1/2 mv squared. In the next context, we didn't make anything speed up. Work done to squish or stretch something. Something elastic. Okay, in this case, the spring wasn't moving before, it isn't moving at the end, and so the work you do didn't make anything speed up. What you did was you squished something elastic. No. All right. Okay, now in this case, when you are squishing something like a spring, the distance to which your force acts, we're going to call that x, but that really is d. And so the work you do, now we cannot use force times distance because it's the force that you're going to use is actually going to grow. The force you have to exert to make this spring compress more and more actually goes up, and you know that because, okay, maybe get a little too detailed here, but there, it's not a constant force. But we showed in an earlier video that the work you do in compressing something is 1/2 kx squared. And we call that elastic potential energy. I forgot to give this guy a title. Okay, so that's one context. This one is, hey, we call that, by definition, we call that K. So kinetic energy is 1/2 mv squared. Got it? Those are our two things. Now we're moving on to the next topic. Now we're going to talk about the third thing that can happen when you do work. And that is doing work. Well, not what can happen, but what happens if you do work against a gravity field? Just think in a place where there's gravity. Okay, so in this case, you've got a box and it has some mass m. There it is. And your goal is to raise it up to this bookshelf. And not surprisingly, it's not moving at the beginning before you do it. Then you're going to exert a force through a distance. You're going to do work. And then at the end, it's not going to be moving either. So in this case, there's no, I'll just jot this down. There's going to be no increase or change in kinetic energy. Now, I'm not talking about the shelf might actually flex a tiny bit. I don't even want to think about that. I shouldn't have even mentioned that. But there's nothing, the box isn't squished. You're not exerting that force through a distance to squish this box. So there's going to be no change in elastic potential energy. But you know that you're going to have to exert a force. This is going to be some amount of force that you're going to have to exert. Oh, sorry. I know. Got to think of something better than that. And you're going to exert that force through a distance, and that distance is going to be the distance between the floor to the bottom of the shelf. And so the work that you are going to do is going to be, and we're going to talk about Well, just say it's your force acting through some distance. Okay, now what force are you going to have to, how much force are you going to have to exert in order to get this thing to move? Well, I want to point out it's not moving at the beginning and it's not moving at the end. So in that case, when there's no motion at the beginning, no motion at the end, we can say that your average force over the course of the lift is going to simply be equal to the weight of the box. Don't believe me? Well, let's look at a force diagram, a free body diagram. Okay, you can say, well, how can it be the weight? If I don't push up harder than gravity, the thing will never accelerate, it'll never speed up, and I'll never get it going. That is absolutely true. So at the very beginning, I will totally concede that you're going to have to push up or pull up with more force than gravity to get it to move. And in that case, it's going to be speeding up. But once it gets going fast enough, you're not going to push with that amount of force. You're going to go back to this amount of force. So in the middle of the push or pull, your force will be equal to the weight. But recall that at the end, this thing isn't going to be moving. So what do you need to do as you get to the end of your push? You're actually going to have to push up with less force to make this thing slow down. So on average, not for everything, but on average, your average force is going to equal the weight. Now, you're going to exert that force through some distance d, but it turns out that when we are changing height by tradition, we don't call that d anymore. We call it h. So there you go. This is the amount of work you do. Remember, what is work? Work is energy transfer. So if you're transferring energy, and if it's not in the form of kinetic energy, and it's not in the form of spring energy, then what is it? It's in the form of gravitational potential energy. So here we go. This is our result. Is if you want to quantify the gravitational potential energy of an object, you simply need to know three things. You need to know the object's mass. You need to know where you are, so you can quantify the intensity of the gravity field. In this case, we're likely going to be on Earth. And then h, where h is the height above some low point. We'll talk about that in the later, but right now I just want to think, let's just say, let's call the floor h equals 0. Okay, so that is the formula for gravitational potential energy. Yes, I can hear you. We see that when you lift something, well, where is it? We see that when you lift something straight up against gravity, the work you do is going to equal mgh. And since work is energy transfer, the energy that gets stored in the gravity field, we'll talk more about that later. But anyway, this energy that gets transferred gets stored as gravitational potential energy. I guess it has the potential to fall down on you and do work on you. It has the potential to become kinetic energy, so then it can run into you. So that's the idea of potential. It can hang around for a long time. Whereas unless you put something in deep space, kinetic energy is doesn't last that long in our everyday life, So that's why I guess we don't call it potential kinetic energy. It's okay, enough of that. So I hear you. That's the work to lift something straight up. So let's look at two scenarios then and see, does it matter which way you go? Does the path that you take when you're going against a gravity field affect the amount of gravitational potential energy? So we're going to look at two scenarios, both involving a box that has mass m. In the first option, we're just going to lift that sucker straight up onto this thing. There's the same box, and we know that the work that's going to be required is going to be mgh, and that means gravitational potential energy is mgh, and that's going straight up against gravity. But what about this option? Suppose that we're going to take that same box with mass m, and we're going to put it on a frictionless. It's got to be frictionless. You start throwing sandpaper in there, and that does change everything. So we either need to think of this as being like on really smooth, nice quality wheels with awesome bearings, or we're just going to say, hey, we're just going to say it's frictionless because we can. Okay, well, will the amount of potential energy change because we're now going up essentially on an indirect path against gravity? And the answer is, let's find out. Okay, so in this case, you are going to still exert a force, and now you're going to exert that force through some distance d. It's not going to be h. This is h. It's going to be the distance of the ramp. And your force is going to be less than the gravity force. Let's see, what is that gravity force going to be? I'm not going to draw the free body diagram, but if this doesn't look familiar, you might want to review it. Is when you're on an incline, the component of gravity that's acting down the ramp is going to be mg sine theta. And so on average, that's going to be your force. At the beginning, you're going to have to push up a little bit harder to get it to move, but at the end, you're going to push up with a little bit less. So on average, the work you do, your average force is, I'm going to have to work on that, is going to be mg sine theta. Now, what is distance d? We know the height is h, but what about the distance d? Well, do you see the right triangle? Okay, well, it turns out that we've got the angle is theta, the opposite side is h, and the hypotenuse is d. So sine theta is going to be h over d, or d equals, swap those guys around, is going to be h over sine theta. Are you seeing it? I hope so, because the distance of the ramp is going to be h over sine theta, and this should give you a nice warm fuzzy. I'm getting one because the sine theta on top cancels out with the sine theta on the bottom, and what are you left with? The work is still going to be mg h. And that's kind of amazing and interesting because it tells you that the work you do against gravity is path independent. That's the term we use in physics. It doesn't matter which way you go as long as you don't have to worry about friction. We'll look at an example on the next page. Okay, this idea that the work you do against gravity is completely path independent, meaning it doesn't matter how you go from some level up to another level, that the work you do is still going to be the same. So let's look at this example. I have a 100 kilogram cart here on Earth, and I want to know how much work required to get this guy to move cart to the top. Now look at this crazy path. There's simply no way I could use Newton's laws. I don't know the angles, okay? But it's so easy because this doesn't matter. I could go this way. I could go this way. I could go, let's see, one more way. What color? I could go this way. There's an infinite number of ways to get from this level. In fact, I don't even have to go here. I can go up here. As long as, it's getting kind of crazy here, but as long as we know the change in height, it doesn't matter how you go from this level to this level, as long as there's no friction. Can't say there's friction. Okay, so this is actually a really, really easy problem because the work that you're going to have to do is going to equal to basically the gravitational potential energy this thing has when it's up at the top. And that's simply going to be mgh. You don't need to know anything. I know it's getting kind of crazy. You don't need to know anything about the way you went. Okay, so all we do is plug in the mass is 100 kilograms. I'm even going to use 10 newtons per kilogram for G. I know because I don't want to use a calculator. Okay, and I know I probably would need, well, yes, I need a calculator because that 25 times 9.8, no way. No, we're going to make it definitely 10. All right, so there we go. That's 100 times 10 is 1,000. It's 25,000 joules. That's how much work. How do I know that? Because that's how much energy you gave it by taking it from this low level up to this high level. All right, that's an introduction to gravitational potential energy.